We're continuing our discussion of the two concentric coils. Remember, in part A, we found the magnitude of the current in the larger coil by looking at the charge at t is equal to 0 plus divided by the capacitance, giving us the voltage divided by resistance. And in part B, the magnetic flux through each turn of the smaller coil immediately after the switch was closed. So we looked at the magnetic field created by the current flowing through the larger coil at the center, and assuming that this magnetic field is uniform, we multiply it with the area of each of the smaller coils to get the flux through each coil. So that's what we did in part B. And then in part C, we found the direction of the current in the smaller coil following Lenz's law. Because the flux in k-hat direction is increasing, I2 must flow in a direction that will oppose this increasing flux. Now, looking at part D, what is the direction of the current in the smaller coil at t is equal to 1.26 milliseconds? Now remember that in part A we calculated the time constant R1 times C. It is 1.26 milliseconds. Therefore, this is asking us to find the direction of the current in the smaller coil at one time constant. Okay, now we know that this is a discharging capacitor, and in this discharge, the current in the larger coil will decrease exponentially in time. So it will be I1 maximum e to the minus t divided by the time constant. The time constant is R1 times C. So at t is equal to 1.26 milliseconds, which is the one-time constant, I1 has decreased. It has decreased so that the flux in k-hat direction, it was creating a flux in k-hat direction, decreases. All right, so I can see that this current is decreasing, the flux it creates in k-hat direction is decreasing. Therefore, I2 must flow in a direction that will oppose the decreasing flux in k-hat direction. So this decreasing flux must be opposed according to Lenz's law. So therefore, we find that I2 at one time constant must flow in a direction that creates a flux in k-hat direction. K-hat direction. So it's opposing the decreasing flux in k-hat direction. Therefore, I2 must flow in which direction to create a flux in k-hat direction? You can see, looking from the top here, I2 must flow counterclockwise. So with the right hand rule, the direction of I2 must change. First it was clockwise to create a flux in minus k-hat direction. Now it must flow counterclockwise in order to create a flux in k-hat direction, opposing the decreasing flux in k-hat direction. So it must flow counterclockwise. So that's my answer to part D of this question. I2 must flow counterclockwise at one time constant in order to oppose the decreasing flux in k-hat direction. Let's move on to part E. What is the magnitude of the current in the smaller coil at t is equal to 1.26 milliseconds? Well, first of all, I know the magnitude of the current in the larger coil at one time constant tau. It is simply the maximum current at t is equal to 0 plus e to the minus 1 t over tau, so it is tau over tau. The current in the larger coil at t is equal to 0 plus was the charge stored Q divided by the capacitance C, that's the voltage, divided by the resistance 2 pi a, the number of turns times resistance per length. And then I have exponential -1 here, so this is multiplied by 1 over E, Euler's number, E. Okay, now at the same time, I can find the magnetic field at time t is equal to tau. It is the magnetic field created by a circular coil with N1 turns, mu0 N1 I1 at its center, twice the radius 2a. And what is the magnetic flux through each coil of the smaller coils? It is this magnetic field, mu0 N1 I1 divided by 2a, multiplied by the area of each of the smaller coils, so pi b squared, the radius squared. Now you can see that the induced EMF in the smaller coil will be equal to minus N2 d phi 2 dt. Why? That is Faraday's law. Okay, now I have to look at this flux and see what is changing with time. What is changing with time is I1 here. So you can see that epsilon 2, the induced EMF in the second coil, is minus mu0 N1 N2 divided by 2a pi b squared di1 dt, because the time dependence comes from the current. The area is constant. Mu0 N1 over 2a is a constant. I have the N2 factor coming from Faraday's law, and I have di1 dt. So I need to know what di1 dt is. All right. So I know what I1 is as a function of time. It's I1 max e to the minus t over tau for a discharging capacitor. So this is going to be di1 dt evaluated at a time constant tau. So that's basically minus I1 max divided by tau e to the minus t over tau. I'm using this result for a discharging capacitor. So that gives me, when it is evaluated at one time constant tau, this is going to give me minus I1 max over tau exponential -1, e to the power -1. So if I substitute for I1 max here, I can see what this should be. di1 dt evaluated at one time constant tau, 1.26 milliseconds, is minus I1 max, which is Q over C, the voltage, divided by the resistance, 2 pi A N1 resistance per length, R1, RC, divided by the time constant tau. What is the time constant? 1 over R1, 2 pi A N1 R, that's the resistance times C, exponential -1. So this gives me, if I perform this calculation, minus Q divided by 4 pi squared A squared N1 squared, resistance per unit length squared, capacitance squared, multiplied with E2 minus 1. Okay, so substituting this result for di1 dt, I can calculate the induced EMF in the smaller coil. That will be 2 minus signs here, 1 minus sign here, 1 minus sign here. They will become plus. So this will be mu 0 N1 N2 Q pi b squared. Q comes from the di1 dt, and this will be multiplied with e to minus 1 divided by 2a times 2 pi a n1 rc parentheses squared. So that's what I have here, 2 pi a n1 rc parentheses squared, and the whole thing is multiplied by e2 minus 1. So what is the current induced in the smaller coil, I2? Well, I2 will be equal to the induced EMF epsilon 2 divided by the resistance of the second smaller coil. Now, if I plug in my induced EMF here, mu 0 N1 N2 Q pi b squared divided by, for R2 I have 2 pi b, number of turns in the smaller coil, resistance per unit length, multiplied with 2a, 2 pi a, N1, resistance per unit length, capacitance squared, e to minus 1. So that's my current. So if I simplify this answer, I will obtain I2 is equal to you can see here there is pi disappearing with this pi, and one of the b's disappear here, and then N2 disappears, and that's basically it. So I will have mu 0. I will also have an N1 cancellation for this N1 squared, so let's take that into account. So I will have mu 0 Q B exponential minus 1 divided by, now you can see I have a factor of 4 here from the square, multiplied by 4. This becomes 16. Then I have an a squared multiplied with a, I have a cube. Resistance per unit length, R multiplied with R squared, giving me R cube. Then I have a factor of pi square coming from this, pi square, and number of turns per unit length squared, but there is 1 on top, so it becomes number of turns per unit length in the first coil. The number of turns of the first coil, not per unit length. And then I have the capacitance squared. So this becomes e to minus 1. So that will be the magnitude of the current in the smaller coils. Okay, so if I calculate this, I2 will be, for mu 0 I have 4 pi 10 to minus 7 Henry per meter The Q was 100 microcoulombs, 110 to minus 6. B, the radius of the smaller coil is 0.04 meters, 4 centimeters. Then I have e to the power minus 1, 16 a cube, 0.4 meters cube. Resistance per unit length, 0.01 ohms per meter cube. Pi squared. Number of turns in the first coil, 5,000, and capacitance 10 microfarads squared. So this gives me an answer for the current in the smaller coil, 365 milliamperes. So that's my final answer for this part of the question. Okay, so let me note here that I've also taken care of this N1, made this N1 squared N1. Okay, so what have we done here? So first we looked at the direction of the current in the smaller coil at a one-time constant tau. Because the current in the larger coil is decreasing due to the discharging capacitor, the flux in plus k hat direction is decreasing, so therefore I2 must flow in a direction that creates a flux in k hat direction, which means it should flow counterclockwise looking from the top. So it must flow counterclockwise. The magnitude of the current in the smaller coil at this instant can be seen by looking at the flux in the second coil, derivative with respect to time multiplied by the number of turns in the second coil, the induced EMF divided by its resistance R2. Now, the current in the first coil, I1, is time dependent. It's I1 max e to the minus t over tau. And when I write the flux in the second coil, I see that it's the magnetic field created by I1, mu0 N1 I1 over 2a, multiplied by its area. The only time-dependent term here is I1, so when I take the time derivative of the flux, I get di1 dt. di1 dt is minus I1 max over tau, e to the minus t over tau. When I plug in I1 max here, and for tau R1 times c, so I note here that tau is R1 times c, I will obtain di1 dt. So plugging in this result for di1 dt in the induced EMF, I can calculate it, and dividing it by the resistance, which is N2 times 2 pi b, the total length of the smaller coil multiplied by resistance per unit length, I obtain I2, the magnitude of the current flowing through the smaller coil, and plugging in the numbers, the answer is 365 milliamps.